everyone, welcome to Try Ride, the new era of learning. This is Pack 365. In Module 2, we are discussing about best first search algorithm in AI. Let's begin the topic. Best first search, informed search. Best first search is an historic search algorithm that selects the most promising nodes from expansion based on an evolution function. It prioritizes nodes in a search space using the heuristic to the estimate their potential by iteratively choosing the most promising nodes. It's aimed to efficiently navigate towards the goal state, making it particularly effective for optimization problems. So here we can say best first search, we called as a BFS2. It has an informed search algorithm used in AI artificial intelligence to find the path from a starting node to the goal node, right? In a graph. Unlike the unformed search algorithm like best first search or depth first search that explores blindly, right? Best first search uses for heuristic evaluation function to estimate the promise of each node, guiding the search towards the goal, right? Here we break down the how best first search works. Okay, so this method is type of the informed or heuristic search, often referred by the greedy search. We also had one another concept also, best first search. We introduced that into next lecture. So it operates by leveraging heuristic values to guide the search process, right? So it's fundamental to the to search the new states like new goals or new nodes existing states to reach the goal state. So it's such the best way of path. The algorithm evaluates the neighboring nodes using a function to determine which one appears the most promising of for exploration, right? So the algorithm evaluates each and every neighbors to it analyzes out which are neighbors were connected to the existing starting point to our existing nodes to explore the overall the path. So a priority queue manage the evolution function cost of the sorry prioritized nodes, right? Each and every function we implement the queue, right? Like first in, first out, mm, FIFO and LIFO, like last in, first out, like that we use techniques. So in queue stack, we enter that concept. If we visit any state, we have mark as visited. If we left over the state, we mark as visited, and the parameters we determined has we already traveled the parameters. Like we mark in each and every state and every parameters. So time and space complexity of the BFF is generally O by V plus in wedges, V plus E nothing but vertical space edges, right? Vertical space edges like nodes plus edges we called as. So where V represents the number of the vertex and E the number of the edges. So alternatively, it is a complexity. It can be expressed as where of B of gray B square D like we can call as B of D like that. So instead of that, we can call it as O of B of D, like okay, O of B of D, like we call B power D, like that. We use the power of the B and D. Yes. So here we have B equal to branching factors, average number of the successor pair node, and D has the depth shallowest goal node. Now, we are given an edge list, right, of the graph where every edges is represented by U, V, W. Here U, V, and W represent the source determination of the weight and edges, and respectively, we needed to pick best first search on the graph, like pick the minimum cost edge next. So we have an example here. So for the example, we take input source has 0. Okay, and our target as nice. Like here we can say input source is nothing but our source like starting goal. Our starting goal is 0 and our target is 9. Like we can say start from 0. Start is 0, initial node, and the target node is 9. So how we can travel the path like edge list. So here we can see that edge list here have 0, 1, 3. In list we have some type of some number of lists here. So we can use this path to travel. It is a like we take it is a standard in table format with like we take the list, right. Like this is the edge list. We each know neighbor how many lists are connected. So like that we can easily travel to our goal state. And we want to print the output has 1, 3, 2, 8, 9. So our input is 0 and target is 9. So we want to output has 1, 3, 2, 8, 9. So here we can start with the instruction. Here we can start with the uh, describe our working example, right? Here we take the example for our best first search. So let's start with that. So come let override that the example, right? So let we start. Our start is 0 and target is 9, right? So what our output 1, 3, 2, 8, 9. So for that we want to start from start at node at 0, right? Among its neighbors, node 1 has the lowest cost, edge cost 3, and so we move further 0 to 1. So here we like we can start like among the its neighbors says node one has the lowest cost, edges cost these three, right? So the search moves from the 0 to 1. This impels a heuristic heuristic that prefers lower edges cost, often used the greedy best search. Like we use here greedy best search. So from node 1, since the better path forward is not available to backtrack to the node 0, is the suggested the exploring the further from uh, node 1 to lead the path that we are not promising has the returning to previous option, or the node 1 had no unvisited neighbor which better than heuristic values. So from node 0, choose the next step, choose the next best neighbor. Node 3 edge cost 5 and move to node 3. Like node 0 still has no node 0 still has other neighbors like, and the evolution function node of the node 3 has the next most promising like that. So at the node 3, find the moving the node 2 led to a lower increment cost. Which indicates that from the node 3 to node 2 is the most promising next step. So then process it for the node 2 to node 8, and finally from the node 8 to node 9 we have target. So here we found the target. The search continues always picking the most promising nodes based on the heuristic until a goal node is reached. So here we can see our we start with 0 and we move to the neighbor of 1, and it among its neighbor to 1 and lowest cost h3. So we move to the 0 to 1. Like here we concluded like the same as we can represent as in greedy search, which is follow the greedy first search method. So we take the mean value of the average. Like if we have three connections for the 0, like 1, 2, 3. In it we choose the mean value. Like if the one we have the 1, we choose 1. After that one we have 4, 5, 6. Like that before 4, like after one we choose 4. Like after that we can move like continuously until our new root node will be reached. Among those, we can say if the value is sometimes we take the direct higher value to reach the fast, but it has a foolish method to try like that. So instead of make the follow sequence and the follow the steps, we can easily identify the our goal state. So, however, let's see in same example. In other here is also we have same example, but here difference is we change the target. Our target is 8. We have edge list and output has we want to print 1, 2, 3, 8. Right? Only 1, 3, 2, 8. In previous example, we have 1, 0, 1, 3, 2, 8, 9. Right? So here our target is 8. So same initialization also start with node 0 among the cross with the neighbors, lowest cost like h the cost 3. So we move further 0 to 1. So from the node 1, since the better forward is not available, backtrack to 0 again. So from the node 0, choose the next best neighbor, node 3, h cost 5. So we can say that and move to the node 3. So at the node 3, find the moving to the node lead to a lower increment cost. So the process from the node 2 to node 8, the target is we found to reach the target. So same example. So approaches. The idea is to use priority quiz or heap to store the cost of the edges that have lowest evolution function values and the operate similar to the BFS algorithm. So we want to follow the below giving steps, like initialize and an empty priority quiz named PQ. Insert the starting node into the PQ while PQ is empty. We can say we can remove the node U, right? With the lowest evolution value of the PQ. If U is the gold node, terminate the search. Otherwise, for the each neighbor U V of U, if V has not been visited, like if V doesn't visited any of the node, so mark V has visited and insert V into the PQ. So mark U has examined and end the procedure when the goal is reached or PQ becomes empty. So same approaches we will find in next also. So this is the concept of the diagram. That we have the S A B C E. We start state is zero. A B C D E F G H I J K L M N O P until not P. We have until with like L and M. We have M up to. So we can say start state is zero, and we want to reach our goal state was I. I or J here we have goal states here. So from diagram, we start from a source S and search for the goal I using the given cost and the best search. So here we start from S and we want to find reach the goal I target I. So for that we PQ installation cost test. So we start from the source S and search for goal I using the given cost and the best search. And PQ initializes contains S, assuming S is the starting node with its initial or heuristic value. And here we remove S from the PQ because it already visited, right? So in the process, unvisited neighbor for the S to PQ. So PQ now contains A, B, C, right? C is an a before because C is put it before. So B because C has lesser cost. So it has a lesser value here, or we can say like that. So this step highlights the order of the priority quiz is based on the evolution function. So we removed A from the PQ and the process unvisited. Neighbor of the two A to PQ. PQ now contains C, B, E, D. Right here we can say that I see the diagram. Here PQ here we contains the A, C, D. Like where it contains C, B. Like A contains S contains A, B, C. Right. So A, C, B. Right. Like how we can take like that. So here C contains H and I and J. So here is the easiest part. If we move C, we can directly reach to the A. So according to we travel from the number C has 7 and like that B has 12 and here A has 9. So we take the lowest number to move forward. So we removed A from the PQ and the process unvisited neighbors of the A to PQ. So PQ now contains the C, B, E, D. The neighbors of A are added in the priority quiz to reorder itself, and we removed C from the PQ and the process unvisited neighbors of the C to PQ. PQ now contains BHED and B is processed B is processed as unvisited. So it contains the HEDF. We removed H from the PQ. It chooses as the most promising. And since our goal I is reached to I is a neighbor of H, we written if I is a neighbor of H and H is the current expanded node. So then the goal is our found. So, like that, we can easily applicants. So, however, once I will explain again the concept of this best first test. So, let us just come from best to BFS is sorry, we have to both BFS in uniform, so informed and uninformed, right? So, in uninformed, we studied as a best first search and depth first search, right? So, in informed, we have best first search and greedy best first search like that. It is an algorithm which uses in artificial intelligence to find the path from starting node to the reach the goals node, right? So the fundamentals of the idea behind the best first search is to expand the nodes that appears to be the best or the most promising at the any given moment. the best determination by evaluation of function, and often a heuristic estimates how the close to the nodes we can easily identify it. So in the algorithm steps, we have initialization steps, inserting the starting node into the PQ, we call it as a PQ. So while PQ is not empty, like that, we have the more initialization states. If our initialization state is the Q, name would PQ. Now in until right now we are calling PQ, right? So that is the PQ is nothing but it is a Q value. We call name Q as PQ. So initialize the empty purity Q. Purity Q, we call purity Q, so we call it as PQ. So a purity Q is crucial because it allows us to efficiently retrieve the nodes with the lowest or highest, depending on the heuristic definition. Evaluation the function of values. In best first search, we typically want to explore the nodes that seems the closest to the goal first. So the priority queue will order nodes based on the uh, heuristic values. Here we are inserting the starting node into the PQ, and the search begins from the specified specific start node we want to choose. While PQ is not empty, then search continues as long as the we will up to explore the all the nodes until we find the goal node. So then we in the process of that is the PQ involves the remove the nodes and evaluation of the nodes here that like considering the best node like it entered. So otherwise, for each neighbors of V and we call if V has not been visited, like something Mark V has visited, like that. Insert into the PQ, explores the unvisited neighbors. So like that, in the end process, when the goal is reached, or PQ becomes empty, or Q becomes empty, then the search stops. Okay. So if the goal found, the nothing to explore, right? We already explored the uh, all the nodes here. So, like the way we use the best first search, I hope you guys this follows the greedy first search method. I also explain that concept in next lecture. So, I hope you guys all of you understand this topic. So, thank you.